We start with a definition right away. So let's assume we have two structures over the same language, M and N. And we also assume that M is a substructure of N. Then M is called an elementary substructure of N if for all L formulas phi with free variables among x1 up to xn and all n elements a1 up to an from M, that formula phi is true in M under the assignment a1 up to an, if and only if it's true in N under the same assignment. Keep in mind that M is a substructure of N, so this makes sense to write this here. So the difference between elementary equivalence and elementary substructure is, of course, first of all, we need to assume here, for this definition to make sense, that M is already a substructure of N. Okay, so, but then the property here is definitely stronger than being just an elementary equivalence, because we now can also look at formulas that are not sentences, but just formulas, and also plug in values from the smaller structure and look at the satisfaction relation with respect to those formulas between N and N. We can extend this, of course, away from substructures to consider the notion of an elementary embedding. That holds if there is a homomorphism between the two structures, and so that the image of that homomorphism is an elementary substructure of N. Right? So homomorphism for structures, recall, that means we can define a mapping that preserves essentially all functions, constants, and relations between M and the image. And if we can choose a homomorphism so that we can actually embed M into the bigger structure, right? So that this relation holds, the elementary substructure relation holds, then we call that an elementary embedding. So we now have two notions that both imply elementary equivalence. We've seen that isomorphism always implies elementary equivalence, but not vice versa. Similarly, as can be easily seen from the definition, being an elementary substructure also implies being elementary equivalent to the bigger structure, because here we actually look at all kinds of formulas, whereas here we would only have to look at sentences. The notion of isomorphism and elementary substructure, in turn, are not comparable, so we can have one without the other one holding or implying. So for example, look at the two structures. One is the natural numbers with the less than relation, and the other structure is the natural numbers. We take out 0 and also look at the less than relation. So these two structures are obviously isomorphic if we map N to N plus 1. Right? But now we could look at the formula with one free variable phi of x, y being not exists x, x less than y. Right? And then if we put y equals 1, then we see that this structure here, N without 0 less than, that satisfies phi of 1. But the other structure, N less than, does not satisfy this phi of 1 here. On the other hand, we will later see that the linear order Q is an elementary substructure of the linear order of R, right? And of course, these cannot be isomorphic simply for cardinality reasons. So we have seen that for being an elementary substructure, a crucial property was that we could actually now address in our formulas specific elements of a structure. It is possible to do something similar or analogous on the syntactical side by introducing additional constants to the language that represent the elements of a specific structure. And that is called the diagram method. So suppose we have an L structure and we extend the language from L to Lm by adding a new constant symbol. So a new constant symbol, Cm, for every m in M. Right? So we just take, for every element in our structure, we just add some constant symbol to the language. Right? And now we're able to address every element of a structure in a formula directly, right? By just interpreting the constant symbol Cm as M. And this way, we clearly can expand a structure M to an Lm structure M sub M, yeah, by interpreting Cm as M. And then we can form two sets of formulas. The one here is delta M. That's the set of all formulas phi Cm1 up to Cmk, where phi is quantifier free. So that's important here. That is a quantifier free L formula. And M1 up to Mk are elements of M such that if I assign M1 up to Mn to these positions here, then this formula phi holds in M. So this is also called, because we are restricting ourselves to quantifier-free formulas, this is called the simple diagram. Whereas the next set of formulas doesn't have such a restriction. So if we look at any L formula here, right, and form the same set of formulas, only we drop the restriction on quantifier freeness, then we get what is called the elementary or complete diagram of M. You can think of a diagram as recording all facts about a structure that you can write down using the symbols in your language. Right? So it's a little bit like a generalization of a group multiplication table, where you also record all the different relations between the elements with respect to the group operation. The nice thing about these diagrams and the extended language is that you can now capture model theoretic notions between structures using the satisfaction relation and the model relation for structures and sets of sentences and formulas. In particular, so let M and N be L structures, and let's assume that M is a subset of M. So the universe of M is contained in the universe of N. Then M is a substructure of N if and only if N, when interpreted as the expanded structure, so we expand the language, add a constant element for every element of M, and then interpret that constant element back as the corresponding element of M, if that structure satisfies the simple diagram of M. Furthermore, M is an elementary substructure of N, if and only if this expanded structure N sub M satisfies the elementary diagram of M. And this then becomes equivalent to the expanded structure being elementary equivalent now. So because we can now actually address single elements of the structures in our language, which we need to express being an elementary substructure, this now we can characterize this via elementary equivalence of those expanded structures here. Again, the proof is of these facts. The proofs are not very hard. pretty much straightforward from the definitions, but as always, I recommend you sit down and walk through the few steps yourself. The definition of being an elementary substructure may seem a little daunting at first, because in order to check it, we need to verify the truth behavior for every formula and for every tuple from the smaller structure. However, this can be greatly reduced to checking only a certain kind of formula and for a certain kind of witness. And this is called the Tarski-Vaught test or criterion. And that test says that A is an elementary substructure of B if and only if for every formula phi in free variables x0 up to xn and n tuple a1 up to an from the smaller structure, if the bigger structure satisfies an existential statement with x0, phi now with assignment a1 to an to the remaining variables, then we can find a witness for that existential statement already in the smaller structure A. So there exists an A0 in A such that B satisfies that statement with assignment A0 up to an. So we can, when checking for being an elementary substructure, we can actually restrict ourselves to just checking this property, this witness property for existential sentences or formulas. And the proof, as usual, I encourage you to try to work this out yourself. So this direction is more or less clear. It follows almost immediately from the definition of an elementary substructure, whereas this direction proceeds by induction on the height of the formula, phi. And most cases, again, are not difficult. Only the case where we do an induction step going from a formula to an existentially quantified formula, that is where we need to do some work. And this is precisely the case where the criterion helps us to make that induction step. The Tarski-Vaught test yields also the following criterion for being an elementary substructure. Namely, if we have A given as a substructure of B, if for all A1 up to AN in A and B in B, we can find an automorphism pi of B such that this automorphism leaves the AIs fixed and moves pi in B into A, then we have an elementary substructure. So again, if we do have a structure B here, and inside this sits A, and we can find an automorphism given a set of a tuple in a finite tuple in A, let's say in this case A1, A2, A3, and a element B in B, we can find an automorphism pi of the structure B, right, that leaves the AIs fixed and moves B into A. And one application of this, and of course you should see that you can verify this theorem, but once you've done that, you should try your hands at this application here, namely proving that the linear order of Q is an elementary substructure of the linear order of R.